Hello, welcome to my video series of data structures. This is part 5 of module 5, the tree data structure. In this video, we will introduce the B tree. In the previous videos, we introduced the binary search tree data structure along with its two advanced variants, the AVL tree and the splay tree. These data structures operate under the assumption that all data is loaded in the main memory. As a result, their time complexity analysis are grounded in this premise, typically based on the number of comparisons or rotations performed within the tree. However, in many cases, the database we have may be too large to be fit entirely into the main memory. In such situations, the database must be stored on a hard disk. Recall that in the implementations of the tree data structures we have discussed, nodes are created dynamically as data elements are inserted into the tree. This approach may result in nodes being assigned with non-contiguous memory addresses, causing their storage on the hard disk become fragmented. For example, the nodes of the tree shown on the left may be stored at different locations in hard disk, as illustrated on the right. In the worst-case scenario, this fragmented storage could require a separate disk access for each tree node. While performing one disk access per tree node may not change the theoretical time complexity, it can significantly slow down the actual runtime. The slowdown occurs because accessing data from a hard disk is much slower than retrieving data from main memory or performing in-register computations. For example, on modern computers, accessing data from an HDD hard drive typically takes about 10 milliseconds, while accessing data from an SSD takes roughly 100 microseconds. In contrast, accessing data from main memory only requires 100 nanoseconds, and an in-register computation takes as little as 0.3 nanoseconds. Now, let's revisit a typical data access operation in a binary search tree and analyze which steps correspond to hard disk access, main memory access, and in-register computation. A data access operation consists of two main steps: visiting a tree node and comparing the target data with the tree node to decide which child to visit next. These two steps are performed recursively until the target data is found or the traversal reaches a leaf node. The first step, visiting a tree node, involves loading the tree node from the hard disk, which requires a disk access. Once the tree node is loaded into the main memory, the subsequent comparison step relies on main memory accesses and in-register computations. Here, we highlight the time-consuming tree node access step in red and the more efficient data comparison step in green. When operating under the model where all data is stored on a hard disk, an intuitive way to speed up data access, such as search, insertion, and deletion, is to reduce computations associated to the rest step. Inevitably, minimizing the overhead associated with the rest step requires increasing the overhead of the green step. However, as long as the additional overhead remains manageable, we can achieve an overall reduction of runtime because the green step runs inherently much faster. So, how to reduce tree node access? We know that the number of tree node accesses involved in a single data access operation is directly determined by the height of the tree. Therefore, an effective way to minimize tree node access is to reduce the height of the tree. There are two strategies to reduce the height of the tree. First, we can increase the number of children per node, which creates a wider and shallower tree, effectively reducing its height. Second, we can store multiple data elements in each tree node, thus reducing the total number of tree nodes and the height of the tree. Specifically, we can increase the number of children per node from 2 to m. Such a tree is called an n-ary tree. In this case, the height of the tree with n nodes can be reduced from log 2n to log mn. Note that as m increases, the tree becomes more shallower. Second, to reduce the total number of tree nodes, we store multiple data elements within a single node. Modern hard disks are organized into many small data blocks, known as disk sectors. During a single disk access, all information stored within a disk sector is loaded into main memory. This approach enables the retrieval of a block of related data with just one disk access. Typically, a disk sector has a size of 4 KB, which is sufficient to store multiple data elements. For instance, a single disk sector can hold approximately 1,000 integer values, though this number may decrease when storing more complex objects. The B-tree data structure incorporates both approaches for reducing the tree height, allowing more children per node and storing multiple data elements within each node. Due to these changes, the B-tree introduces its own data organization and tree traversal rules, which differ from those of the binary search tree and its variants. Below, we will delve into the details of the B-tree, focusing on its search, insertion, and deletion operations. First, we present the definition of a B-tree. A B-tree must satisfy 5 key properties, defined by 2 parameters, m and l. M is the maximum number of children each node can have, while L is the maximum number of data elements that can be stored in a single tree node. L is also referred to as the load of the leaf node. The 5 properties are as follows. First, the data elements are stored in the leaf nodes. Second, the non-leaf nodes store up to n-1 keys in ascending order to guide the search. The ith key represents the smallest element stored in the i+1th subtree. Third, the root is either a leaf or has between 2 to m children. Fourth, all non-leaf nodes, except the root, have between the ceiling of m/2 and m children. Finally, all leaf nodes are at the same level, and they store between the ceiling of L/2 and L elements. Here we have an example of a B-tree with m equals 4 and L equals 3. This means that in this B-tree, each non-leaf node can have at most 4 children, and each leaf node can store up to 3 data elements. To simplify the presentation, we label the non-leaf nodes as A, B, and C, and the leaf nodes as T1 through T7. Let's verify the 5 properties of the B-tree one by one. First, we confirm that all data elements are stored in the leaf nodes. Second, we verify that the ith key in a non-leaf node corresponds to the smallest element stored in the i+1th subtree. For example, the first key in the root node, highlighted in blue, is 25. This value is also the smallest element stored in the second subtree of the root node, which is rooted at node C. Similarly, the second key in node B, highlighted in purple, is 12. This value is the smallest element stored in the third subtree of B, which corresponds to the leaf node T3. The third property specifies that the root must have between 2 to m children. In our example, the root has 2 children, which satisfies this requirement. The fourth property specifies that all other non-leaf nodes, except the root, must have between the ceiling of m over 2 and m children. When m equals 4, this means that non-leaf nodes can have between 2 to 4 children. In our example, all non-leaf nodes meet this requirement. Finally, the fifth property specifies that leaf nodes must store between the ceiling of L over 2 to L data elements. When L equals 3, this means that each leaf node can store between 2 to 3 data elements. In our example, all leaf nodes satisfy this condition. Now that we have defined the 5 B-tree properties, we can proceed to discuss its search, insertion, and deletion operations. Let's start with the search operation. Given a target X, the search process begins at the root node. We perform one disk access to load the information stored in the tree node into the main memory. If the current node is not a leaf, we examine its keys to determine which subtree to visit next. Specifically, we compare X with the keys in the node and identify the smallest index I such that the ith key is greater than X. We then proceed to visit the ith subtree. If X is greater than all the keys, we visit the last subtree. This step involves comparing X with all keys in the node, leading to a time complexity of OM. On the other hand, if the current node is a leaf, we search for X among the data elements stored in the node. If X is found, we report success. Otherwise, we report X is not present in the tree. This step involves comparing X with each data element in the leaf node, resulting in a time complexity of OL. In summary, at each phase of the search operation, exactly one disk access is required to load the current node into main memory. Then, depending whether the node is leaf, OM or OL time is required to compare X with the keys or the data elements in the current node. To illustrate the search process in a B tree, let's walk through an example by searching for the value 15. First, we load the root node into main memory. We compare X with the key stored in the root and find that X is smaller than the first key. According to the definition of the key in the B tree, the smallest element stored in the second subtree of the root is 25. Since our target X is smaller than 25, it cannot be present in the second subtree. Therefore, we proceed to examine the first subtree of the root. Next, we load node B into main memory and compare X with the key stored in this node. X is smaller than the third key, 18, indicating that X is smaller than the smallest element in the fourth subtree of B. Therefore, we proceed to examine the third subtree. Next, we load T3 into the main memory and find that this node is a leaf node. Since it is a leaf, we search for X among all data elements stored in this node. Finally, we find 15 and report that it is present in the B tree, terminating this search. Next, let's explore the insertion operation in the B tree. Suppose we want to insert the value 4 into the B tree. Similar to the binary search tree and its variants, the insertion operation in the B tree traverses the tree in the same manner as the search operation to locate the correct position for insertion. To insert the element 4, the process begins by loading the root node into memory and comparing 4 with the key stored in the root. Since 4 is smaller than the first key, it cannot present in the second subtree. Therefore, the insertion continues in the first subtree. Next, we load node B and find that it is a non-leaf node. We compare 4 with the key stored in B and determine that the insertion should continue in the first subtree. Then, we load the node T1 into memory and find that it is a leaf node. We check whether there is an empty slot available in this leaf node for the insertion. Fortunately, this leaf node still has one empty slot, allowing it to accommodate the new element. In this case, the new element 4 is inserted into the leaf node T1. After updating the content of the leaf node, the modified data is written back to the hard disk using one additional disk access. Suppose we continue to insert a new data element, 27, into the B tree. Following the tree traversal rules, we determine that the new element 27 should be inserted into the leaf node T5. However, we find that T5 is already full and has no empty slot to accommodate the new element. In this case, we attempt to push one element from the current leaf node T5 to one of its neighboring leaf nodes. If we push to its left neighbor, we select the smallest element in the current leaf node. On the other hand, if we push to its right neighbor, we select the largest element in the current leaf node. In this example, we find that the right neighbor of T5, T6, has one empty slot. Thus, we push the largest element in T5, which is 28, to T6. After pushing 28 to T6, both leaf nodes T5 and T6 now contain 3 data elements each, satisfying the B-tree property. Note that the minimum element stored in T6 now becomes 28. Therefore, we need to update the corresponding key in its parent node B accordingly, as highlighted by purple in the figure. At this point, the insertion is complete. When we cannot push any element from a full leaf node to any of its neighbors, inserting to that leaf node can trigger a series of node splits. Now, suppose we want to insert another element, 16, into the B tree. Following the same tree traversal rules, we know that the new element should be inserted into the leaf node T3. However, T3 already contains 3 elements, which is the maximum allowed capacity. Note that both of T3's neighbors, T2 and T4, are full. Therefore, we cannot push any element from T3 to its neighbors. To handle this, we split the full leaf node T3 into 2 new nodes, T31 and T32. Each of the resulting nodes will contain half of the original set of data elements. Specifically, since the maximum number of data elements a leaf node can hold is L, a split is triggered only when the node temporarily contains L plus 1 elements. After the split, each node contains the ceiling of L over 2 nodes, ensuring the B-tree property. In our example, a new leaf node T32 is created by the node split, which must be attached to a non-leaf node to maintain the tree structure. Based on the keys stored in node B, we determine that T32 should be attached to B as its 4th subtree. However, this creates a new problem. Attaching T32 to B increases the number of B's children to 5, exceeding the maximum capacity allowed by the B-tree property. To handle this case, we perform another node split. Unlike the previous split, which involved a leaf node, this time we split a non-leaf node. A non-leaf node split is triggered when the non-leaf node temporarily contains m+1 children. After the split, the resulting two non-leaf nodes will contain at least the ceiling of m/2 children. This is why the B-tree property specifies that each non-leaf node, except the root, can have between the ceiling of m/2 to m children. In our example, the non-leaf node B temporarily contains 5 children and is split into two non-leaf nodes, B1 and B2. B1 contains 3 children, and B2 contains 2 children. Now, there are 3 non-leaf nodes at the second level, B1, B2, and C. To accommodate this change, we adjust the keys in the root node A to properly attach all 3 non-leaf nodes. Since the root node can contain up to 4 children, this adjustment satisfies all B-tree properties. With that, the insertion operation is complete. Note that in some cases, a root split may be required, as highlighted in the red box. When this happens, we create a new node, such as the purple node R shown in the figure, to serve as the parent of the split nodes. The new node R becomes the new root of the entire tree. After a root split, the new created root will have exactly 2 children. This is why the B-tree property allows a root node to have as few as 2 children. At last, let's discuss the deletion operation in the B-tree. Suppose we want to delete the element 15 from the B-tree. The deletion operation begins by following the standard tree traversal rule to locate the element in the tree. In our example, we find 15 from node T3 and proceed to delete it. Deleting 15 from T3 does not violate the B-tree property, because each leaf node is allowed to hold as few as 2 elements when L equals 3. Since all B-tree properties are maintained, the deletion is complete. In some cases, deleting an element may reduce the load of the leaf node below the minimum threshold allowed by the B-tree property. For example, if we continue to delete 3 from T1, T1 will be left with only one element, which is below the minimum threshold, 2. In such cases, we can borrow a data element from one of the neighboring leaf nodes, provided that doing so does not reduce the neighbor's load below the allowed minimum. When borrowing from the left neighbor, we take the largest element. On the other hand, when borrowing from the right neighbor, we take the smallest element. In our example, T1 can borrow data element 9 from its neighbor T2. This adjustment ensures that both leaf nodes comply with the B-tree property. In some cases, borrowing an element from a neighboring node becomes infeasible, as it will cause the neighbor's load to drop below the minimum threshold. For instance, imagine that we continue to delete the element 1 from the B-tree. After deleting 1, the first leaf T1 is left with only one element. It cannot borrow any element from T2, as T2 already contains the minimum of 2 elements. In this case, we should perform a node merge, which is the inverse operation of a node split. The two leaf nodes, T1 and T2, are merged into the leaf node T12. as highlighted by the red box. When a no merge is triggered, one leaf node must have a load just below the minimum, while the other leaf must have exactly the minimum load. In other words, one leaf node, such as T1, should contain the ceiling of L over 2 minus 1 data elements, while the other leaf node, such as T2, should have the ceiling of L over 2 data elements. Hence, merging these two leaf nodes result in a new leaf node containing either L or L-1 data elements, such as T12. The load of the merged leaf node falls within the valid range defined by the B-tree property. After merging the two leaf nodes, the number of node B's children is reduced. In this case, we adjust the keys stored in B accordingly, as highlighted by the red box. Since B contains a valid number of children after the no merge, the deletion can be terminated at this point. However, similar to insertion, a single deletion may also trigger a series of no merges, propagated from the leaf level up to the root. Non-leaf nodes can be merged in the same way as the leaf nodes. When a merge is triggered, one non-leaf node must contain the ceiling of m over 2 minus 1 children, while the other must contain the ceiling of m over 2 children. Merging these two nodes will result in a new non-leaf node with n-1 or m children, both of which are permitted by the B-tree property. In the boundary case, a series of recursive no merges may reduce the number of children of the root node to just one. For example, as shown in the figure, the entire subtree highlighted in gray shading is deleted, leading to this scenario. In this case, since the root node contains only one child, all traversals must proceed to that child. As a result, there is no need to retain the root to guide the traversal, and we can safely delete the root. In our example, we would delete the root node A in this case. The only child of the root, such as the purple node B in our example, now becomes the new root. Now, let's analyze the time complexity of the search, insertion, and deletion operations. As discussed earlier, the number of disk accesses required by any of these operations is bounded by the height of the tree. Given n data elements, with each leaf node storing up to L data elements, the total number of leaf nodes is in O n over L. For an n-ary tree, the total number of nodes is proportional to the number of leaf nodes. Therefore, the total number of nodes in the B tree is also O n over L. Hence, the height of the tree is O log m n over L. This means that for each data access, the number of hard disk accesses required is O log m over L. After retrieving a tree node from disk, we need to examine the keys or data elements stored in the node. Specifically, examining each key in a non-leaf node requires OM time, while examining each data element in a leaf node requires OL time. Therefore, the overall time complexity for each data access operation, such as search, insertion, and deletion, is O log m n over L times O max mL. Finally, let's discuss how to determine the parameters m and l. Recall that m defines the maximum number of children for each non-leaf node, and l defines the maximum number of data elements stored in each leaf node. The values of m and l should be determined based on the size of each disk sector, denoted as D, and the size of each data element. First, each leaf node must hold up to L data elements. Therefore, the size of a single data element multiplied by L must be less than or equal to D. Second, each non-leaf node must hold n-1 keys and m pointers to its children. Assuming each pointer requires 64 bits, or 8 bytes, the size of a single data element multiplied by n-1 plus 8 bytes multiplied by m should be less than or equal to D. When both constraints are satisfied, the larger the values for m and L, the less hard disk accesses are required for each search, insertion, or deletion. In summary, we have discussed the B-tree data structure in this video. B-tree is designed under the computation model where the database is too large to fit entirely into main memory, making disk access necessary to retrieve tree nodes. Since accessing the hard disk is much slower than in-memory access and in-register computation, the primary goal of the B-tree is to minimize the number of hard disk accesses. To achieve this, the B-tree reduces the tree's height by allowing more children per node and by storing multiple data elements in a single node. Unlike the binary search tree and its variants, such as the AVL tree and the split tree, which store data elements in both leaf and non-leaf nodes, the B-tree only stores data elements in the leaf nodes. To ensure that the B-tree properties are maintained after insertions and deletions, we follow a series of recovery steps. If the current leaf node is able to accommodate the insertion or deletion, that is, no overflow or underflow, we can directly insert or delete the element without further adjustments. Otherwise, if the current leaf node cannot accommodate the insertion or deletion, we first attempt to resolve the issue by seeking help from the neighboring nodes. For an overflow caused by insertion, we try to push an element to a neighbor. On the other hand, for an underflow caused by deletion, we try to borrow an element from a neighbor. If help from neighbor is not feasible, we perform no splits for overflow or no merges for underflow to recover the B-tree properties. With these mechanisms, the B-tree properties are maintained, ensuring efficient data access without loading the entire database into the main memory. Thank you for watching and see you next time.